We know that every linear transformation from a vector space V to a vector space W can be represented by left multiplication by a matrix once we choose bases of V and W. So maybe it's not surprising that to find the eigenvectors and eigenvalues of a linear transformation, we can just do that by examining a matrix. Now the matrices corresponding to linear transformations from a vector space to itself are square. So let's let A be an n by n matrix with real entries. If there is a vector V in Rn and a scalar lambda in R such that AV equals lambda V, then we say that V is an eigenvector of A with eigenvalue lambda. And I should mention only the non-zero vectors V having this property are interesting. Because if you multiply a matrix A times 0, then that always equals a scalar times 0, because we have 0 equals 0. So we always have A times 0 equals lambda 0 for any scalar lambda. So only the non-zero vectors V with AV equals lambda V are interesting. So for example, let's look at the matrix A, which is 2 times the identity matrix. All vectors in R3 are eigenvectors of A with eigenvalue 2. That's because if we take 2, 0, 0, 0, 2, 0, 0, 0, 2 times A, B, C, we get 2A, 2B, 2C, which is 2 times A, B, C. Another example is, let's let A be the matrix 1, 2, negative 2, 2, 1, negative 2, 0, 0, 1. Now A times 1, 0, 0 is 1, 2, 0. So we can see right away that not every vector in R3 is an eigenvalue of this matrix. 1, 0, 0 is not. It doesn't get mapped to a multiple of itself. A times 0, 1, 0 equals 2, 1, 0. I guess 0, 1, 0 is not an eigenvector either. A times 0, 0, 1 is negative 2, negative 2, 1. So I guess 1, 0, 0, 0, 1, 0, 0, 0, 1 are not eigenvectors. but a times 1, 1, 0 equals 3, 3, 0. So that means that 1, 1, 0 is an eigenvector with eigenvalue 3. So there are some eigenvectors, they're just not the natural basis elements. All right, so now to find eigenvectors, first we find eigenvalues. And I claim that the eigenvalues of A are the solutions of determinant of A minus lambda I equals 0. That is determinant of, so we take the matrix A and subtract lambda from all of the diagonal entries. And then we just keep the entries of A everywhere else. So just take A and subtract lambda, subtract lambda, subtract lambda everywhere on the diagonal. I'm sorry, I went off the end a little bit, and that last entry is ANN minus lambda. So the only difference between this and A is the diagonal, where we subtract lambda from each of the entries in the diagonal. So we set determinant of that matrix equal to 0 and solve for lambda. All right, so what does that have to do with eigenvalues? This equation doesn't make it clear. So the reason is that eigenvectors satisfy AV equals lambda V. V equals 0 always satisfies this, but again, that's not interesting. Now, A lambda equals lambda V if and only if AV equals lambda V, if and only if AV minus lambda V equals the 0 vector. That is, AV minus lambda identity V equals the 0 vector. That is, A minus lambda I V equals the 0 vector. So this is some matrix times a vector equals 0. This equation always has B equals 0 as a solution. Again, that's not interesting. And this is the only solution if A minus lambda I is invertible. That is, if its determinant is non-zero. It has more solutions if its determinant is zero. So that's why we want to solve determinant of a minus lambda I equals 0, to find solutions to this equation that are not just the zero solution. So then once we find eigenvalues, let's say lambda 1, lambda 2 up to lambda n, we solve a minus lambda 1I v equals 0, a minus lambda 2I v equals 0, etc. to find eigenvectors for each. All right, these last words are for each, which I guess I can fit right here, for each. So each eigenvalue is going to give us an equation that helps us find an eigenvector having that eigenvalue. So let's do an example with the matrix I used before. Let's use A equals 1, 2, negative 2, 2, 1, negative 2, 0, 0, 1. So determinant of A minus lambda I equals determinant of, we just write minus lambda everywhere on the diagonal, and then copy the matrix as it was everywhere else. Now the determinant of this is, oh, I see two zeros here, so why don't I expand on the last row, plus, minus, plus, minus, plus. This is going to be 1 minus lambda determinant of this upper 2 by 2 matrix. One minus lambda 2, 2, 1 minus lambda. So that's 1 minus lambda times 1 minus lambda squared minus 4, which is 1 minus lambda times 1 minus 2 lambda plus lambda squared minus 4, which is 1 minus lambda times lambda squared minus 2 lambda minus 3, which is 1 minus lambda. Let's see if we can factor this. Lambda minus 3 times lambda plus 1, I think works, because we've got minus 3 lambda plus lambda is minus 2 lambda. Okay, so it factors that way. I'm going to leave it factored because we want to set this equal to 0 and solve for lambda. So this is 0 when lambda is one of the numbers 1, 3, and negative 1. So these are the eigenvalues. All right, then to find the eigenvectors, we're going to solve A minus each eigenvalue times the identity times a vector equals 0, and then we'll solve for the vector. So let's find eigenvectors for lambda equals 1. So we'll solve A minus 1 times the identity, V equals 0, which is, so we'll just subtract 1 from the diagonal, so we get zeros on the diagonal. 0, 2, negative 2, 2, 0, negative 2, 0, 0, 0, V1, V2, V3 equals 0, 0, 0. Sometimes we need to do row operations to solve this, although this example is so easy. Well, the last equation just disappeared. Now we've got 2v1 minus 2v3 equals 0. So that only happens if v1 equals v3. And then the first equation says 2v2 minus 2v3 equals 0. And that only happens if v2 equals v3. So v1 equals v3 and v2 equals v3, then all of the components have to be equal. Let me leave the matrix there. Therefore, the solutions are t, 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 where t is a real number. So 1, 1, 1 is one eigenvector. And so is any multiple of that. All right, then we can look for the eigenvectors for eigenvalue 3. So let's find eigenvectors for lambda equals 3. So we subtract 3 from the diagonal, and we get 1 minus 3 is negative 2. Copy the rest of the matrix. Negative 1 is the next eigenvalue that we need to find. I'll put that in a box here. Alright, so these equations are sort of easy to solve too. The last equation says v3 equals 0. And then if v3 is 0, the second equation says 2v1 minus 2v2 equals 0. So that means that v1 equals v2. And then the first equation says minus 2v1 plus 2v2 equals 0. So that's the same thing. v2 equals v1. So the solutions are anything, anything, 0. The first and second components have to be equal. And t can be any real number. So 1, 1, 0 is one eigenvector. And so is any multiple. Because t could be any real number. And then let's find eigenvectors for lambda equals negative 1. So find eigenvectors for lambda equals negative 1. So we'll subtract negative 1 from the diagonal. Subtracting negative 1 is adding 1. So we'll solve two diagonal entries are 2. Copy the other entries, -2, 2, -2, 0, 0, v1, v2, v3 equals 0, 0, 0. And again, we've got 2v3 equals 0, so v3 equals 0, and then 2v1 plus 2v2 equals 0, which means that v1 equals negative v2. So that means the solutions are, let's see, v1 equals negative v2 and v3 equals 0. So t negative t, as t varies through all real numbers. So one eigenvector is 1, negative 1, 0. So any multiple of that also. So maybe we should try that. So the original matrix, here we go, 1, 2, negative 2, 2, 1, negative 2, 0, 0, 1. So our eigenvector for the eigenvalue 1 was 1, 1, 1. I'm sorry, that wasn't for 1, 1, 1. That was, oh yes it was. So 1 plus 2 is 3, minus 2 is 1. 2 plus 1 is 3, minus 2 is 1. 0 plus 0 plus 1 is 1. And then we got 2, 1, negative 2, 1, 1, 0 for the eigenvalue 3. 1 plus 2 plus 0 is 3. 2 plus 1 plus 0 is 3. 0 plus 0 plus 1 is 0. And then for negative 1, we have this eigenvector. 1, 2, negative 2, 2, 1, negative 2, 0, 0, 1 times 1, negative 1, 0 equals 1 minus 2 plus 0. So it's negative 1. And then 2 minus 1 is positive 1. 0, 0, 0. So this vector gets mapped to 1 times itself. This vector gets mapped to 3 times itself. And this vector gets mapped to negative 1 times itself. And the eigenvalues are 1, 3, and negative 1. Now each time we did the example, our answers had t in it. So any multiple of these vectors would work. Let's think about that issue. Why does any multiple of an eigenvector, and this is always going to happen, make a good eigenvector? So why do we have a choice of any multiple? Well, the reason is an eigenvector is a solution of a minus lambda I v equals 0. That is, it's in the null space of a minus lambda I. And since the null space is a vector space, it's closed under scalar multiplication. So if we look at it that way, I guess it's not too surprising that a multiple of an eigenvector should be an eigenvector also. The end.